Very warm welcome to all our enthusiastic listeners joining us from India and across the globe for the day 4 of the World Space Week 2025. As you all know, the topic of the World Space Week 2025 is living in space. I am your host, Amoli, and I'm delighted to be a part of this evening on behalf of Propagation team. And before we begin, I would just like to tell you something. Please keep your microphones off during the session so that the talk is complete without any hindrance. Secondly, if you have any questions, kindly post them on the chat or just raise your hands after the session is over. The talk is over. Now, as you all know, World Space Week is the world's largest annual celebration of space and science technology observed all over the world from 4th to 10th of October. This year's theme, Living in Space, invites us to imagine how life can adapt, survive, and thrive beyond the Earth. So far, this week we have explored astronaut training, citizen science, and astrobiology, each session helping us understand what it means to live beyond Earth. And today, we continue that exploration by turning our gaze towards one of the most mysterious stars in the sky, that is Betelgeuse. Now, I would like to also inform you something about the organizers. The Propagation Institute for Advanced Studies is a global platform connecting students, researchers, and educators in the pursuit of discovery. And in collaboration with the SS Citizen Science Group, which is India's largest citizen science community, we aim to bridge learners and scientists, ensuring that curiosity never stops at the classroom. And it is this shared curiosity that brings us all together tonight. Now, let me introduce all of you to our eminent guest. She is a decorated speaker and a decorated scientist. We are actually really honored to welcome Dr. Priya Hasan, an astrophysicist whose career embodies the spirit of exploration. She is an assistant professor of physics at Maulana Azad National Urdu University, Hyderabad, with a PhD in astronomy from Osmania University and postdoctoral work in France and at IUCA, Pune. A DST Women Scientist Awardee 2006 and US Consulted IVP LP Fellow 2011. She has lectured at MIT, Harvard, and Caltech. Her research covers star formation, star clusters, and galaxies, and she serves on the international team of the 30-meter telescope. She also leads initiatives as co-chair of the IAU Women in Astronomy Working Group and Regional Astronomy Education Coordinator for IAU OAE, inspiring countless students worldwide. Introduction to the topic of today. She'll be talking about, Dr. Priya Hasan would be talking about the Betelgeuse mysteries resolved. Unravels the cosmic drama surrounding the red supergiant Betelgeuse, which mysteriously dimmed in 2019 and 20, prompting speculation of an imminent supernova. But what truly happened? Dr. Hasan will decode the phenomena, shedding light on what this tells us about the life and death of massive stars. Ma'am, we would definitely like to hear from you. And the mic is over to you. Thank you, ma'am. Most
Thank
welcome.
You so much. Yeah. Thank you so much, Amoli. Thanks for the kind introduction. And thank you, Propagation Institute, for inviting me and giving me a chance to talk to everybody. And so I'm going to start sharing my screen. So it worked.
Yeah.
Okay. So thank you very much. And thanks, Amoli, also for introducing and for everybody for bearing with me. What I'm going to talk about today is Betelgeuse. This is a star that any amateur astronomer or anybody, if you look up at the sky, you've definitely learned how to identify Orion, right? Orion is one of the most easily identified constellations in the sky, which you specifically see in the winter sky. You have the three belt stars which make the belt of Orion, which you can see over here. And here up here at the right shoulder is where you have Betelgeuse, right? So that's a star which people can identify very easily and very, very well. And that was very good because this is a very interesting star. If you actually see, it's a huge star. We can see over here, its size is compared to the size of our solar system. So what you can see is that if this is our solar system, you can see it's almost the size or even beyond the size of Jupiter's orbit, right? This is a huge star. It's a really very big star, and that's why it's called a red giant. Okay, it's a red giant, and so that's the size of the sky. And now we're going to talk about not just being big; it's still a very interesting object, and let's continue talking about that. So the purpose of this talk obviously is Betelgeuse. Like I told you, it's an interesting star, very interesting star. But it's also a very interesting story to tell because this actually shows you how science develops, how discoveries are made. Because science is not something that is sitting in your textbook, which is waiting to be studied. It's a process of discovery. For you and me, even us as astronomers, we are constantly discovering things. And by in this talk, what I want to actually show to you is how does the scientific process actually develop? Because that is very well demonstrated in this talk, where I'll show you how people's perception of what was actually happening with Betelgeuse, how that changes. So you have a combination of observations as well as theory, and a play between these two things, which actually shows how science builds up, right? So I hope to show that to you in this talk today. So let's start off with Betelgeuse, the data about the star. This is what is called a red supergiant star of the type M1, M2, 1A. Don't worry too much about that. It's about 700 light years away from us, not very far away. It's a relatively close affair, and it's what is called a semi-regular variable. Okay, since when stars become red giants, they basically expand, right? And because they expand to such large sizes, you see its radius is almost 1,000 times the radius of the sun. And therefore, what happens, the outer layers, the outer layer of the sun is about 6,000 degrees Kelvin. But because this star has swollen up to a size of about 100 times that, so therefore what happens is the star actually becomes cool, right? So the surface temperature of Betelgeuse is only 3,600 Kelvin, right? It's much cooler than the sun because it's basically all expanded. It's massive. It's a very massive star. It's about 17 to 19 times the mass of the sun, and its luminosity is of 100,000 times. It has a rotation period of 17 years and an age, we understand it pretty well, to be about 7 to 11 million years. Okay, so that's the star, the data about it. And like I showed you at the very beginning, is it's big. It's a very big star. It's one of the largest stars visible to the naked eye. So here you can see in a picture, it's compared to some of the stars which some of you may know. For example, if you know Sirius, that's one of the brightest star in the sky after the sun. And you see Aldebaran, Arcturus, and Taurus. Betelgeuse is bigger than all these other stars. It's a really very large star. And because it's very large, what happens is the luminosity of a star, the brightness of the star, depends upon the radius of the star as well as the temperature. Okay, so if you have such a large star like this, it becomes very, very bright, right? And therefore its luminosity is very high. That means you can see the star very easily, obviously with your naked eye, and even under various conditions, you can actually, even in a bad sky, you can actually manage to see Betelgeuse, right? So it's one of the largest stars you can see with your this thing. Now, the interesting part about this star is that you can see very clearly, if you actually look at the brightness of the star, it varies. So such a star is obviously called a variable star. So what you can see is you can clearly see that there's a period. You can see this period, right? But nature behaves slightly differently. Nature doesn't exactly give you, a postcard kind of image. You can see, but there's very clearly a periodicity, right? You can very clearly see the periodicity of this star, right? And so basically what people, when they try to fit it to different, time periods, they fit it to various periods, like one of about 2,200 days, which is like 5.5 years, one of 420 days, one of 230 days, one of 185 days. So there are various periods which they try to fit this to, depending upon how they, plotted these points. This is what is called a light curve. A light curve is the variation of brightness of a star with time. Right? So you can see it's definitely periodic, but these are the 4 approximate periods which people this thing. We know that because it's a red giant, it also has various, dark patches, something like the sunspots, which we have in the sun. And sunspots are basically regions which are cooler regions on the surface, right? So you could have some of that's the thing with a real star, that you have the play of the periods Along with that, you have other factors which add in more, more spice to the whole thing. So you have, for example, you have these sunspots. These are huge sunspots, not the kind like on the sun, but much larger ones. And they are regions of cooler ones. So suddenly you may have a dip in brightness, as well as since the star is in a giant phase, you could also have bright blobs of rising gas, right? So you could have various fluctuations in this periodicity. It doesn't sit so nicely, basically because you could have the dark spots which are coming in, as well as you can have these bright spots, right, which add into the confusion, right? So here you can see a video of the star. So what's very clear, what you can see in the star is these are what are called pulsating stars. Okay, pulsation means the size is increasing and the size is decreasing. Now, why is this basically happening? You know that a star basically has nuclear reactions, right? So due to the nuclear reactions, the star is bright, and that gives you an outward pressure. Along with that, you have gravity, which gets it inward, right? So what happens is that when you have this nuclear reaction taking place, the star becomes very hot and the star kind of expands, right? As the star expands, the outer surface becomes cooler, so the nuclear reactions reduce, and therefore the star kind of collapses a little bit because the nuclear reactions have reduced because the star has become a little cold. So it becomes small. And then as it becomes small, again it becomes hotter, again it triggers off the nuclear reactions, and again it expands, right? So these are what are called pulsating stars, and giants are often pulsating stars. And what makes them very interesting is that these pulsations are actually, there are certain Cepheid variables, where the pulsations has a period luminosity relationship. That means if you have the period, you can actually calculate the absolute luminosity of this object, right? And if you know the absolute luminosity of the object and you know the apparent luminosity of the object, you can use that to find the distance to the object, right? Another important thing is that obviously the luminosity, if you're getting the actual luminosity of this object, it is an indicator of the mass of this object, right? Because the luminosity depends upon the mass of a star. The more massive a star, the more luminous it's going to be. So these pulsations which you see are basically the curve which you see, as well as, like you can see, there are also these spurts of gas being thrown out and the spots and all, which add to the confusion. So what happens, we say Betelgeuse is a pulsating red supergiant. It physically expands and contracts, like I told you. And when it becomes the smallest, it is about the size of the orbit of Mars. Okay, that's small. And then when it expands, it goes the size of Jupiter's orbit, what I showed you in the very beginning. So you have this kind of variation taking place, right? Now, the primary pulsation, which we fit this to, is about 420, 425 days, right? But like I told you, you had these larger pulsations also. The largest one being 5.9 years, right? Now, the confusion was that which of these periods is related to the pulsation of the star, right? Any of these periods which we have could be related to the period of the pulsation of the star. Is it 420 days or is it 5.9 years, right? 2,200 days. Which one is the underlying frequency or the period which is coming because of the star? So that's normal, that's fine. Betelgeuse is a very interesting star, so amateur astronomers can keep observing it, and you can note the brightness on every given day, and then use that to actually plot it and plot the light curve and see how does the brightness of the star change. Okay, now why the noise? So the noise started in sometime in 2019. Okay, this is COVID times. This is rather slightly before COVID times. But it was kind of those times also. So October 2019, January 2020, this is about the time when suddenly this star suddenly became very faint. It started becoming very faint. So it began to dim, and it dropped by a factor of about 2.5, about 3 times the thing. And from the brightest 11 star, it became the brightest 21st star, right? So you can see this dip over here, which you can see. So you have this normal oscillations, and suddenly here you have a dip. Okay. So Betelgeuse used to be as bright as Rigel. Rigel is this star, which is diagonally opposite to Betelgeuse. Okay, this is Orion, the 3 stars which make the belt. The redder star is Betelgeuse, and the bluer star is Rigel, which is like diagonally opposite. They are approximately the same brightness. But what you can see over here by 2019, December 2019, this is what Betelgeuse looked like. And Rigel, you can see, is much, much brighter than that. While in general, it's generally as bright as that, right? But then it suddenly became so faint. Okay. And so people obviously made a very big noise about it because this star is in what is called the red supergiant phase. And that is the phase after which massive stars like Betelgeuse, which is like almost 20 times the mass of the sun, they go supernova. Okay. So people actually made so much of a noise because they thought, is it time for Betelgeuse to go supernova? Is it, it's kind of the lull before the storm, and has it dimmed down so much that it's going to go supernova? So before that, let's ask a question: what is the supernova? Before that, we'll even ask the question: what are stars? I'm sure many of you all have watched Lion King, and in Lion King, the two favorite characters are Timon and Pumbaa. So you see Pumbaa asks Timon, "Ever wonder what those sparkly dots are up there, the stars?" And Timon says, "Pumbaa, I don't wonder. I know." Pumbaa says, "Oh, what are they?" Timon says, "They are fireflies that got stuck up in that bluish black thing." So Pumbaa says, "Oh, gee, I always thought they were balls of gas burning billions of miles away." So Timon says, "Oh, Pumbaa, with you, everything's gas." So if you've actually seen the movie, you'd actually understand the context. But very beautiful movie. So typically, here's the definition of the star, which actually, if you see Timon got it, Pumbaa got it right. They are balls of gas burning billions of miles away. So what you have is, this is a big ball of gas. There's nuclear fusion taking place at the center, and but the kind of nuclear fusion that takes place differs depending upon the mass of the star. And this basically happens because if you're a very massive star, then through gravitational collapse, it can collapse to a small size, due to which the star becomes very hot. While if it is not a very massive star, it collapses but doesn't reach a very high temperature. So the kind of things which happen. So if you actually look at the sun has a luminosity, already has an age of 4.5 billion years. Trust me that that's the number. And it gives out a luminosity about 4 into 10 power 26 watts. Okay. 10 power 26 is 1 followed by 26 zeros. So typically, if you see the sun's energy, which is released in 1 second, this could actually power India for 9 million years. Okay. That's the amount of energy you're getting out from the sun. So a star, what is a star? A star is basically a nuclear reactor. Okay. So what does a nuclear reactor do? A nuclear reactor, like the kind we build on the Earth, we actually do what is called nuclear fission. We take heavy atoms, for example, uranium-235, and you break it into smaller atoms. And when you break it into smaller atoms, energy is released, and that's what is called the energy from nuclear fission. Fission is when you break from big to small. What stars actually do is exactly the opposite. They do fusion. So they start off with hydrogen. Hydrogen is the lightest element. And then you fuse that to form helium atoms and heavier atoms. So if you know a little bit of physics, you will know that this is what is called the binding energy curve. That means if I bind, basically it means that if I have two atoms, A and B, and I join them together, right? What I end up with is I get another element called AB, but the mass of AB is lesser than the individual masses of A and B, right? So the excess mass is what we call the mass defect. And that mass defect, if you multiply into C squared, we call that the binding energy. And that is the energy which comes out when you do either, this is the part when you do nuclear fusion, and here is the part when you do nuclear fission, right? So either you do fission or you do fusion, and you do it like that. The only problem is if you're doing fusion, then you need very high temperatures. You need a temperature of at least 1,000,000 degrees to actually do fusion. But if in fission, we do not need that. And that's the kind of processes we use in our nuclear reactors. So typically what stars do is you have a core, and the core is basically hydrogen, and this hydrogen burns. What is hydrogen burning? The simplest process is what is called the proton-proton chain. Supposing you have 4 protons, hydrogen atoms, you actually join them together to get a helium nucleus. So you can see the initial total mass of the 4 protons is 6.693 into 10 power minus 27, but the resultant is lesser than the sum of the individual masses. So this mass is about 6.645, right? This is lesser than this. And the difference is what I call the mass defect, which you can actually, which is this. If I multiply this into C squared, I will get the amount of energy which is given out in a single proton-proton chain, right? So this is what is called the proton-proton chain. And this is the basic reaction which happens in the sun. So 91% of the sun's energy comes out from this proton-proton chain. Other than this, you could also have what is called the CNO cycle, carbon, nitrogen, oxygen cycle. And then you could also have the helium burning or the triple alpha reaction. So it's very simple maths. Your helium is 4, you multiply that into 3, you get 12. So therefore, 3 helium will give you 1 carbon, right? So what the stars basically do is that they fuse smaller atoms to give you heavier atoms. So you start off with hydrogen, you get your helium. Then from your helium, you can then add it on to get you carbon, you can get oxygen, you can get nitrogen. So you then just add up all these, atoms, all the electrons, protons, etc. And that's how you build up heavier elements. You can even have carbon burning that to give you further things. So what basically the star does is it fuses all these lighter elements to give you heavier elements. And like I told you, the only difference is that in these reactions which we spoke about, the proton-proton chain is the slowest reaction. It's very slow. It takes place at a very slow. Yeah. Yeah, so the proton-proton chain takes place at a very slow pace, but these other reactions take place much, much faster. And therefore, we have a very strange thing which happens, that the lifetime of a star is inversely proportional to its mass. So what happens if my star is very massive? It manages to get very hot temperatures in the core. So it does very efficient nuclear reactions, due to which it burns its hydrogen, helium, etc. very fast, due to which its lifetime becomes shortened. Okay, so this is slightly counterintuitive. You would assume that if I had a big fuel tank, it will burn for a longer time, while a small fuel tank will burn for a shorter time. But in this case, what happens is my big fuel tank, it like burns much faster, and therefore it gets finished much faster than the small fuel tank. So you can see that a star, which is about 40 times the mass of the sun, can live just for 1,000,000 years. But for example, a star which is 15 times the mass of the sun, something like Betelgeuse is slightly more massive. It can only live for 12 billion years, maybe 10 billion years, 10 million years. A million is 10 power 6. Billion is 10 power 9. So a star like our sun actually lives for about 9 billion years. So you see, this is a factor of 3. This is 1,000 times longer it lives compared to, for example, the Betelgeuse, right? So 15 times, this is approximately this thing. It would be about 10 million years, but the sun is about 9 billion years, right? So you can see that low mass stars, they actually live much longer than high mass stars. Okay, so what do? Once they finish burning all their hydrogen, then they start burning. So that is what is called the main sequence lifetime of a star. Then it starts burning helium. So it moves towards the right. Why? Because in the right, this is what is called the HR diagram. Here is the brightness and here is the temperature. So this side is hotter, this side is colder. So what happens? The star finishes burning its hydrogen. Then it slightly cools down because it swells up. Okay, it becomes a giant. So it becomes cooler. It's cooler over here. It becomes brighter. Like I told you, because the radius increases, it becomes brighter. And then it starts burning its helium. It starts burning its carbon, and it basically occupies this region, which is called the red giant region. Okay, so now it's fusing not hydrogen. It fuses hydrogen only in the main sequence. But when it goes here, it starts fusing helium and carbon and all other heavy elements over here in this region. Okay, so you start off with the star at hydrogen, then you start burning the hydrogen, you get helium. Then in the core of this, you burn the helium to get carbon. In the core of this, you burn the carbon to actually get oxygen. In the core of this, then you go to heavier elements, for example, neon. So you get this onion shell-like structure, okay? And this continues till the level of iron, okay? After iron, if you want to fuse elements, you actually need to provide energy. You will not get energy, okay? So till then, till this point, it is an exothermic process. After iron, it is an endothermic process. That means you have to provide energy. So stars can fuse up to iron, and it gets this onion shell-like structure. Okay, so this is typically what has happened with Betelgeuse. You fuse still heavier and heavier elements. And then what happens is you end up with all these shells. Okay, so let's see, for example, the sun. What happens with the sun? The sun started like a protostar. It is at present in this stage, which is like what we call a main sequence star, which is basically burning hydrogen. Then it will become a red giant after some time. When it finishes burning its hydrogen, it will swell up. And then what happens is the outer regions, they actually escape. Okay, because there's nothing to bind them, they escape. And the central part, the core, will stay on to become what is called a white dwarf. And this will take about 4.5 billion years, okay, 10 power 9. So this is a long time from now. Don't worry, this would happen after 4.5 billion. None of us will be there. And you'll just have the core left over here. These outer parts will. This is what is happening with the sun, because sun is not a very massive star. Okay, so that's how it would be as a red giant. So when the sun swells up as a red giant, it's going to go up to the orbit of Saturn. All the planets will be engulfed. So it obviously includes the Earth. But high mass stars, Betelgeuse is a high mass star. In Betelgeuse, what happens is it's finished its main sequence phase. It is now a red giant. But now, because it's so very massive, the outer regions, they start expanding. The inner part is a core. And there's a big rift between these 2 points. So what happens is you have what is called a supernova. That means there's suddenly a blast where the outer shell is thrown out from the star, and you'll only have the core sitting right in the center. This whole thing, these things. If the star is very massive, then the core can become what is called a black hole. If it's not very massive, it will become what is called a neutron star. So this is the fate of a high mass star, which is typically the fate of Betelgeuse. So we'll come back to Betelgeuse now. Like I told you, this is the HR diagram where we have the main sequence, the giants, the supergiants, and the white dwarfs. Okay. So now the current state of Betelgeuse. What is the state of Betelgeuse? Typically, to fuse hydrogen to helium, it takes about 10 million years. Okay. If you remember, we said that Betelgeuse has crossed that time. It's like 11 million years. To fuse helium to carbon doesn't take very long. It's about 500,000 years. Okay. Carbon to neon is about 600 years. Neon to oxygen 1 year. Oxygen to silicon 6 months. And then silicon to iron is 1 day. And then after that, you'd have boom, which is your supernova explosion, right? So now when we actually observe Betelgeuse based on its pulsation modes, there are different pulsation modes. We actually think that Betelgeuse seems to be fusing helium into carbon. It's at this stage, okay? It's basically at this stage of its life, which is fusing helium to carbon, okay? We have evidence of this, that this is what is basically happening. But you can see that you have these different shells where different fusion reactions are taking place. Now, what is going to happen to Betelgeuse? We know a star like this, if it is in this phase where it's about helium to carbon, 500,000 years, it's still doing that. So at least it has about 100,000 years to finish this thing. And then what will happen? The iron core will collapse. It will form the core. And Betelgeuse will blow up as a supernova. And the core will most probably become a neutron star. And the supernova will be so bright, it will be as bright as the moon. You'd be able to see it in daylight also. And it's something that we're all very much looking forward to. So if you actually see the brightness of Betelgeuse and the time since the explosion, this would it be. This is when you have the supernova, this thing. It would be approximately the brightness of the full moon. And then it will gradually fade, but this is over days. So you see 100 days, 1,000 days is like 3 years. In 3 years, it's going to come down like this. But otherwise, for a good amount of time, for at least 100 days, it's going to be about as bright as the full moon. And then it will slowly drop in its brightness. This is going to be a spectacle which all of us actually look forward to seeing. We do not know whether we'll actually see it in our lifetime, but it'll be a very beautiful thing to be seeing. Imagine you'll have a second moon up there in the sky, which you could actually look up to. So the question was that if Betelgeuse actually goes supernova, if it went boom, what would actually happen to us? So like I said, it's going to be as bright as the full moon, but it's quite far away from us, okay? So actually, when a supernova blast takes place, there's a shock wave which will actually move, right? But because the distance of Betelgeuse is about, it's about 130, 150 parsecs, it's quite far away from us. So the shock wave, which will actually move at a speed of 13 kilometers per second, okay, that's the speed. The shock will stop outside the Earth's orbit. So it's actually not going to hit us. So it's actually dangerous for us if we have a supernova within 10 parsecs. Then we need to worry. But this one is not so bad, right? So we are safe, nothing to worry. And a lot of people, when this dimming happened and people got worried, people were wondering as to what's going to happen. But then people were still exploring and looking for evolutionary tracks, seeing that how long, and estimates were there that it would take about 100,000 years for the supernova to go, and it's not going to happen now. But the problem was Betelgeuse was dimming, right? Remember I told you it suddenly became so faint, it started becoming very, very faint, and people did not know why is this fainting happening. Okay. And therefore, then there were spectroscopic studies done where they realized that the temperature of Betelgeuse has not dropped. It is about the same temperature. There are ways we have to estimate that. And they did not, it was barely, they didn't find any temperature drops. And therefore, there are various reasons, observations, which are called spectrophotometry, where you're basically looking at the star in different filters, in different wavelengths, to actually see what is actually happening to the star, right? And therefore, they came up with this. There were various telescopes all over the world, which were actually observing it and trying to see, right? And basically, they realized that there was some episodic mass loss, okay? This is just, we know that the sun also throws out mass like that, coronal mass ejections, but this is a much more massive star. And there was some kind of episodic mass loss which took place. And then you can look at this. This is a real image of Betelgeuse using a telescope called the ALMA telescope, the Atacama, Atacama millimeter array. And you can clearly see that there's a bright spot, and you can see that the star seems to have a little bit of a lopsided shape, right? This was found with the image. There's another image here. You can see this is taken with the VLT, the Very Large Telescope. This is an infrared. And again, over here, you can see that there seems to be some structure, okay? And basically, it was realized that there was some amount of gas that had been thrown out from the star. And you have, again, images of the star. This is January 2019, December 2019, January 2020, March 2020, where you can see here the fading is taking place. And you can clearly see that there's some kind of this dust, which is down here, which is actually formed over there. So people with all basis of all these images, this is what they think basically happened. That basically there was some large amount of mass which was thrown out from the surface of the star. And because of that being thrown, you had a lot of gas and dust which was formed, okay, because of the throwing of this thing. And this is the dust. And when we looked at it from the Earth through the dust, we actually saw this black patch over here. So you can see that almost half the surface of the star got covered by the dark patch, which actually caused the fall in temperature, okay? So this is what happened, and was the most accepted explanation for the dimming of Betelgeuse. So this is just some self-propaganda. You can actually Google this. This has been published by me in Resonance. Resonance is a journal of the Academy of Sciences. So this was published in 2020, which is the whole story of this thing, where actually it ends with the thing that basically the dimming of Betelgeuse was because of an event like this and not because of an incoming supernova event. So the story continues. This was happened in 2019, 2020. Obviously, people now built up more interest in Betelgeuse and were trying to look that, okay, if it's dimming, now what's happening after that, okay? And therefore, they tried to, this is another telescope called Stereo, which actually basically looks at the sun, okay? Its job is to look at the sun, but it was actually used to also look for Betelgeuse and basically measure the brightness. And you can see again, this was the dimming, the great dimming. And you can see once again, Betelgeuse suddenly kind of brightened up, okay? So that's what people noticed, that it kind of brightened up. There was another Japanese satellite also, which was used to look at Betelgeuse. And the advantage with this satellite is that it could follow Betelgeuse at all times and actually give us a brightness measurement, okay? So you can see that here, this is the great dimming, which I was talking about, 2019, 2020. And then you can see very well, by 2020, by the mid-2020, the star again became its usual brightness. These are two different filters, the V filter and the B filter, but the star suddenly again became bright enough. And now again, you had the usual fluctuations, which you can see till 2025, right? We have similar fluctuations, but you can see this great dimming which happened has risen up and the star kind of became normal. So people said, oh, that means the prediction we had made that this was just a dust thing, nothing to do with supernova, is most probably true, because now the star seems to have come back to normalcy. So that's what they this thing, that, okay, you actually see it. But then the star, something seemed to be happening to it. If you were putting the 420-day pulsation, you can see it fits so nicely in the past. Then suddenly when we had the dimming, then it kind of missed the pulsation, right? So the question was that, will it resume? What happened to the, the regular pulsation which we had with Betelgeuse? What actually happened with it? People were totally confused. And then we had this interesting paper which came out from a Japanese group. And like I said, you have these different periods, 2,200 days, 420 days, 230 days, 185 days. And if we generally assume that the pulsation of the star, you can see over here, this is the 420-day period. The pulsation of the star is caused by the 420-day period, right? And basically on that, you can make a mass estimate, okay? Now, this group, what they said is that, no, it's not the 420 days, it's the 220 days. That is the pulsation period, this period. This is the pulsation period, which is the primary pulsation period. And based on that, they made an estimate that Betelgeuse has this kind of a mass, 11 to 12 times the mass of the sun. And if it was 11 to 12 times the mass of the sun, then if you remember, I showed you those periods which are required for fusion, etc. Then in principle, Betelgeuse had finished this period. That means Betelgeuse is already ready to go supernova, or it's already gone supernova. It's about 600, 700 light years away from us. So even if Betelgeuse goes supernova today, we will only get to know that about after 600, 700 years, right? So the question was that, has it already gone supernova? And if you actually look up on the net, you will find a lot of talks and articles by people where they actually said, oh, probably Betelgeuse has already gone supernova, we're just not seeing it as yet, right? So if there's 2,100 or 2,200 days, fine. Then in that case, it's in the last stage and you're ready for supernova. That's what was done by this paper. But there was obviously, there were other researchers which had actually used other techniques to estimate the mass of Betelgeuse. And for example, there's this other paper by Joyce et al. And they said, no, the what you're getting with that earlier paper cannot be true. We cannot take the 2,200-day period as the primary one. We should take the 421, because that gives us a mass of about 764 MSUN. And in that case, if that is the day, then we still have time for the supernova to take place. So there was this confusion. Now, while all this confusion was there was a new proposal made by people in 2025, where they actually said that, oh, one way of explaining this, the two periods which you have, 420 and 2,200, is yes, let's say Joyce et al. Are correct. 4,200 is because of the pulsation, but the 2,200 period, the day period, is because of a companion. Okay, so this was actually proposed by this group, Morgan McLeod, etc. And they said, oh, this is most probably the reason for the the variation. And so if you actually look at the variability studies, you see that because it's a bright star, we have more than 100. So what these people actually did, they actually used data of more than 100 years. Okay, and that's basically because the star is so bright that even it can be seen with naked eye, right? So if you actually see, we have very good old data, which actually shows you variability from 1893. Okay, and like they saw these periods vary from 400 to about 2,000 days. And they said, no, you have these two periods, but 400 is the pulsation period and 2,200 is the companion period. And then in 1993 was the first time when people actually tried to take a first direct image of the surface of the star using the faint object camera on the Hubble Space Telescope. And with that, they could actually estimate the size of the star. So why is that important? Because in these estimates, which we are making of the pulsation, etc., the estimate of the radius of the star will also give you an estimate of the mass of the star. So that could what got people more convinced that the 420-day period maps better to the mass of the star and the size of the star, like what we got from the direct image, right? So people began to believe that what Sao and all had got using 2,200-day period, instead the 420-day period is more correct. It matches better with the mass and the size estimates of Betelgeuse. Okay, so then there's the possibility of this companion. Okay, now there were also various other observations done by this group also, where they actually saw that there's some kind of a hot spot on the star which actually varies with time. And when there was even infrared imaging done of the star, you can see that there are variable hotspots. There are hotspots on the surface of the star, which are, kind of moving, seen with various telescopes, etc. Even in ultraviolet, in spectroscopy, again, they tried to see what are the kind of brightness variations on the surface, etc. And then we had an image we done with ALMA. This is a millimeter telescope, which actually it confirms that the UV axis orientation, that there's some kind of variation in the brightness. So now using these periodicities, these are that 2200 is called the long secondary period, where this mechanism was used to observe to detect it. So now the new story was that is this a companion, right? But obviously finding the companion for a star like Betelgeuse is very, very difficult. Why? Because this 2200 days, it's about a 6-year period, right? So the problem is that if the star has an orbital period near six years, it's relatively close to the star, right? And you know that Betelgeuse is so super bright, right? It's a very, very bright star. And obviously, depending on the brightness difference, most probably that star is not going to be as bright as Betelgeuse. Otherwise, we would have seen it as a binary, right? We don't see it as a binary. So you have Betelgeuse being so bright and this companion being so faint, and obviously it would be difficult to observe. So it was tried out with the Hubble Space Telescope as well as with the Chandra X-ray telescope. So they both observed it and they could not find the companion. But one result they could get from that because they could not observe it, sometimes a negative result is also good, because they could not observe it, that implied that this star is a low mass star. If the companion says it's a low mass, most probably it's a young stellar object, because they could not see it on ultraviolet. Okay, so a young stellar object is a very young star which will be bright in infrared but not in ultraviolet, right? So that's why they came to a conclusion that if there is a companion, the companion has to be a low mass young stellar object. It's not a compact object because it was not observable in X-ray, right? And it should have a low mass, whatever it is. And then we have this very brilliant team, Steve Howell. Many of you all may, I don't have a picture, but there's a very standard book which is used by astronomers to study CCD astronomy, which has been written by Steve Howell. And so these are observers, and they decided that let us try observing, actually looking for this companion in what we call direct imaging, that is try to observe it. Okay, but obviously direct imaging is a very difficult job, like I told you, because Betelgeuse itself is very bright. So how do you get to actually observe it? Right. So they use this telescope which you see on the right over here, which is the Gemini North telescope, and this has a diameter of about 8.1 meters. Okay, that's the Gemini North telescope, which you can see on the right, and they use this to actually look for it. Okay, so if you actually notice, I hope you're seeing the dates. This is very, very recent. This is like happened 2 months ago. This was in August 2025. So they can distinct this, and what they did was, this is a Gemini North telescope. There's a Gemini North and a Gemini South. So what is the technique they used? So I would like you to appreciate the technique they have used. So what happens, why do stars twinkle? When you look at a star, for example, the light from the star, you know that if you're on the earth over here, you have the atmosphere. In the atmosphere, you have turbulence, and you can have pockets of hot and cold air, right? Due to which there's refraction on the light which comes from the star, it gets refracted. That means what is refraction? Is just the deflection of light, right? So the light kind of moves left, right, left, right. So when you look up at the star, the position of the star keeps varying, right? Because of this shifting, depending upon the positions or these pockets of hot and cold gas between you and the star in the atmosphere. This only in the atmosphere. So because of this, what happens? These things shift and the star twinkles, right? So ideally speaking, if you were looking at a single point, you would actually see a single star. But in reality, what happens is because of turbulence, you get multiple images, okay? The image of the star keeps shifting. And what happens, it shifts so fast that your eyes, when they look at it, it kind of adds up all these images. So the star, instead of looking like a point object, it looks like a blurry thing, okay? A blurry disk like this. Now, they used this group, Steve Howell, etc. They used a technique called speckle imaging, okay? Now we, like I told you, because of turbulence in the atmosphere, the position of the star keeps changing, right? What your brain does is it adds up all these images and looks at a blurry thing and tells you that's the star. So it's not a point source, it's one blurry thing, right? Speckle imaging, what they do is instead you take a large number of short exposures, okay? So you're trying to take exposures which are of the order of a millisecond. I think I have the this thing, yeah. So you can see over here, they could be like 60 milliseconds exposures or 10 millisecond exposures. A millisecond is 10 power minus 3, right? So you're taking 0.006 seconds or 0.001 second, right? So you take very, very short exposure images, basically so that the shift in position of the star, which is happening because of changes in the atmosphere, you can avoid the shift. So you end up with single shots, you know, I'm moving my hand, but you get points, this, you get my hand moving at different points, right? So instead of getting a whole thing where my hand is this big disc, you are going to get the individual shots of my hand at different positions, right? So in principle, if you had a binary star, for example, in this case, if I have this is Betelgeuse and this is the other one, both of them are going on shifting their things. So when I look at them, I just see both of them together. I do not resolve them as two stars, right? But what is done in speckle imaging, you're taking many short exposures. And then what is done is what is called lucky imaging. Lucky imaging means of the short exposures you get, you select the ones which are good images, okay? The ones that have got distorted because of turbulence, etc., you chuck them out, you don't use them. You use the ones which are good, which is called lucky imaging. So of the, how many ever exposures you took, for example, here you can see, you had 562 nanometers, you have 6,060 millisecond exposures. And at the other band, which is 466 nanometers, they had 6,010 millisecond exposures. So of the 6,000 images, you choose the ones which are good. And then once you've chosen the ones which are good, you can overlay them together, stack them up together. So then that will add up the photons, right? So you stack them up together only for the good images. And once you stack them up together, right, you can actually use that to get this image. So this is a real image which they got with the Gemini Naught telescope, which you can see very well. That's Betelgeuse, nice and bright. And you have the blue-white companion star, which shows up over there, right? Now, in principle, this technique is really very beautiful. You are actually pushing your telescope to its maximum, things that you can get with it. And they actually found out over here, you can see, the stellar companion, they had actually calculated it already. So they actually found it out that it has an angular separation position angle of 52 milliarc seconds. It's about 115 degrees east of north. And, they actually found the thing. So that's our thing. Only problem is that as per calculations, when we actually do observational data, we look for a signal which is at least 3 times more than the noise. Okay. So that is the statistical way of actually validating the data that you get. So generally, whenever we have data which we want to, use for a certain purpose, it should at least be 3 times more than the signal. But obviously, in this case, because Betelgeuse is so bright and this companion is very faint, therefore the sigma detection, we call this the sigma detection. This is only a 1.5 sigma detection. It's not 3. Okay, it's a 1.5 detection, but through calculations earlier, it exactly fits into the predictions. What people had predicted was the position of the thing, angular separation, magnitude difference, etc., estimated mass, all this which was estimated earlier, it actually matches very well with those estimations. And therefore, though it's a 1.5 sigma detection, in principle, we can take it with a pinch of salt and we can assume it to be fine. So in this case, what we have is about, this companion has a mass of about 1.5 times the mass of the sun. It's a pre-main sequence star, like we said earlier. It's about 6 magnitudes fainter than Betelgeuse and orbits close to Betelgeuse. Instead, it's so close to Betelgeuse that it's kind of within Betelgeuse, okay, this companion. And that is why, so people then decided, call it Beetle Buddy. So it was actually named Beetle Buddy. So if we actually look at the kind of data we have, if this is the size of Betelgeuse, we can see that this guy is kind of within the envelope of Betelgeuse, right? It's flowing within that envelope. And therefore, this was also used as a possible explanation for the great dimming, that you have this star which is within the envelope of Betelgeuse, right? And therefore, in 2019, probably when this, mass ejection happened, right? Probably there was something of the interaction also with this star, which actually caused it to, kind of escalate, in the sense to dim to such a strong extent, so that we actually had this great dimming event taking place, and all those effects. So you actually, it probably fits in quite well with the great dimming event too. So if we actually, let's talk again about HR diagram. If you remember, I showed that to you in the beginning, the HR diagram. If we, on the HR diagram, we place these two stars, the companion is somewhere over here. It's a pre-main sequence star. It's not yet sat on the main sequence. But Betelgeuse is somewhere here. It's a post-main sequence star. It's a giant. It's sitting over here. But if both these stars form together, you remember a long time back, I even showed you a thing about the ages of stars, and depending on their mass. So typically, Betelgeuse is about 10 million years. And if this star is about 1.6, 1.5 times the mass of the sun, it's obviously too young to sit on the main sequence. It's a pre-main sequence star. So if these guys are coeval, if both of them form together at the same time, then that is their position on the HR diagram. And because this star is Betelgeuse actually means the hand of the giant. Okay, so I used AI, ChatGPT, to actually generate this image for me. Betelgeuse is actually the hand of the giant, and this is a companion to it. So people decided to name it Sivara. Sivara is the bracelet of the giant. So the companion is the bracelet, while Betelgeuse is the giantess rather. Betelgeuse is a giantess, a female giant. And here we have Sivara, which is the thing. So if you remember, I told you that this one has this 1.5 sigma thing, which is not typically in the scientific community. We want a better number, at least 3 sigma. So what actually happens is that these were observations done in 2025, right? The period is about 5 to 6 years. So the assumption is that in 2025, these stars were away from each other. And now in another 2.5 years, these stars will move on the other side. It won't complete an orbit. It'll exactly do half an hour orbit. So they will be at what we call longest elongation. That means furthest away from each other, easy to observe. And that's what we expect, which will happen in about 2.5 years, which is November 2027. And now that we have all this data, etc., a whole bunch of big, good telescopes are again going to once again attempt to directly image this companion star. So we hope that by November 2027, right, when there's the next greatest elongation, not just Gemini North, which is 8 meter, we have even more larger telescopes. And we also have the James Webb also. And we do hope that many of these much larger telescopes will actually try to look for it and, validate it and get a better value. So I also wrote another resonance article describing this thing, because like I told you, what I like most about it is the story of how does it show you how science unravels, right? Starting off with the story of the pulsation and the dimming, and then the proposal about the companion and how we validate it. And even to this date, since it's only a 1.5 sigma, we are still looking for a better estimate. So we still want to further validate it. There is a chance of it being wrong, but we are inclined to think that it should be right. But all this is very well described in another article, which I've submitted to Resonance. It has not yet got accepted, but keep watching out for it. Hopefully it will get accepted and you'll get to read this article where this is described in much more detail. So that's the wait and watch game which we have to do. And this is the scientific method, which hence, because of the way you see it evolves, it's therefore very exciting, because you always have new developments, new observations, new theories. Like the theory got proposed that, okay, it could be a companion. Maybe it can be something else. We don't know. It waits for further validation in terms of observations or other people validating it in some other way, which will explain why and how we got this, these kind of observations for it. So we look forward to that, and let's see what happens with the Betelgeuse enigma. Let's see how it gets further resolved, and we look forward to that. So thank you so much. I'll end with that, and I'll be happy to take questions.
Thank you, ma'am. It was really an insightful session. Enjoyed it, every bit of it. So knowledgeable. Really didn't know about the beetle buddy.
But this is very, very recent. This is like end of
Yeah.
August. It's just very,
Yeah.
very.
Yeah. So I would like to take some questions.
Yeah.
We have a question from Shabi Q. What's your name? I'm really sorry.
Sabika, I think.
Sabika. Yes. You may ask your question. Please unmute yourself. Sabika, kindly unmute. Yeah.
Okay. First of all, good afternoon.
Yeah. Hi.
And
Good evening. Isn't it evening?
Ma'am, the
okay.
participants are from all over the world.
Okay. Okay.
Okay,
Fine.
good evening. Okay, my question is that since Betelgeuse sudden dimming was later understood as a combination of dust and ejection, surface cooling, possibly magnetic activity, could you explain how multi-wavelength and inframetric observation helped confirm these causes? And what life cycle of massive stars near supernova, also considering the unpredictability of such stellar behavior?
Okay, 1 minute. So one was your about temperature estimation, right? And the second
Yes,
question,
yes.
what is the second question about? Hello, Sabika. Okay. Okay, fine. So temperature estimation is done in a very simple way in astronomy. I think I showed you. It is called spectrophotometry. What we basically do is that we look at the object in different wavelengths. So in observations, that means you see it in different filters. Okay. And typically a back body spectrum looks something like this. Okay. So what happens is if you have the brightness of the object in more than one filter, right, then we can actually fit that to a black body curve, assuming it to be a black body, and we can actually look and say what should be the temperature, right? So typically, if you have a hotter body, right, if you have a hotter body, it will emit more in shorter wavelengths, okay? So supposing I have two filters, one is a short wavelength, one is a long wavelength, right? So if it's emitting more in the shorter wavelength than the longer wavelength, then it is a hot body, while if it is emitting more in the longer wavelength compared to the shorter wavelength, it's a colder body. Okay, so that's the basic idea, but typically you observe it in different wavelengths and you can actually use that to estimate the temperature. So why was that important? Because the question was that if there was to be a supernova, which was ready to happen, then there should have been a sudden change in the temperature, right? And that's when you would expect the supernova to take place, because there'll be a sudden change in temperature. But what was found is that there was no change in temperature. That means the surface seemed to have about the same temperature, which actually, therefore, the idea was that probably it's not a supernova blast. It's just this dust which is coming, which is actually blocking the light, which is causing the dimming, right? So in that way, that fits with our observations. Yeah.
Okay, thank you
Okay.
so much.
Thank you, ma'am.
Okay.
And the next question from Ashwin sir.
Yeah.
Ashwin sir, kindly unmute yourself.
Sorry, Amoli ma'am, I raised my hand by accident.
Okay.
Yeah, I don't have a
Okay.
question right now. Yeah, sorry.
No problem.
Okay. Thank you. The next question I'll be taking from the chat. It's from Krishna Singh. Why, after making iron, star nuclear fusion stops? Is it because of iron is stable, or we don't have much energy?
Okay, thank you. That's a very good question to ask. So basically what happens is that, see, when you're doing nuclear fusion, obviously two atoms are going to repel each other, right? They have electrons in their outermost orbit, and therefore, when you push them together, they repel each other. Okay, but only when you have hot enough temperatures can these two atoms collide and fuse together to give you a heavier element. So typically, you need very high temperatures for that to happen. Obviously, as the atoms become heavier and heavier, right, the repulsive forces between these atoms is going to be more and more, right? So typically, you will have a, say, 1 billion degrees Kelvin. In that, you can still fuse carbon and nitrogen, etc. But then as you go to heavier elements, for example, iron, by then the amount of electrons in the outermost orbit are so much that these two iron atoms, if you try to fuse them together, they do not fuse. In the sense, you cannot manage to get them together, right? So in general, if you go less than iron, you can still manage it. And the process is what is called an exothermic process. That means when you fuse it, you will get energy outside. But if you want to fuse iron more than heavier than iron, for example, you want to get gold, right? But if you want to get gold, what happens? A normal star cannot do it because you won't be able to fuse those atoms to join them together to give you gold. So that will only happen in a supernova blast. So typically, if you have a supernova blast taking place, then there's a lot of energy which is emitted. And when that excess energy is there, which is emitted, that's when you manage to fuse elements heavier than iron, which basically explains what we call the abundance. Why do we have up to iron? There's plenty of that on the earth. We have lots of it because stars normally fuse it and it comes from there. But heavier than iron, like for example, gold, platinum, etc., for these you need to have a supernova thing. And we know that nature, what nature does is nature basically produces more low mass stars and less high mass stars. So the number of supernovae blasts you have happening is very little compared to the number of low mass stars. So what happens is, because you do not have so much of supernova blasts, so you don't produce gold, which makes it expensive and precious, gold, platinum, etc. So up to iron, you can do it comfortably. It's an exothermic. After that, you have to provide. So you have to have some kind of process, for example, a supernova, or even now there are things called kilonovas, or more, exotic energy providing processes, which will give you heavier elements. So producing heavier elements is tougher. The universe is basically hydrogen and helium. So it can fuse those lighter elements much more easily than the heavier ones. Yeah.
Okay. The next question coming up from Ananya Das. What determines that a star becomes a white dwarf, neutron star, or a black hole?
Yeah. So thanks again. So basically, that's the mass of a star. If you have a star which is like the mass of the sun, then what happens is the central core, it kind of shrivels up, and the outermost thing kind of just disperses into the outer medium, and it forms what is called a planetary nebula. That means it just kind of fades out like a cloud, and it doesn't create much of a boom about it. It just goes out like that. So that is if the star is of the mass of the sun. If it is more massive than that, for example, 8 times or 10 times the mass of the sun, then it will have a supernova. Okay, like for example, Betelgeuse. Then you'll have a supernova event. And there are different places that have different estimates. Often people put 8 or 10 is the estimate to have, then the core will become what is called a neutron star. If it is more than that, 15 or 20 times, then it becomes a black hole. But there are different ways of calculating it. But something like 10 will give you a neutron star, and more than 15 or something will give you a black hole. So it all depends upon the mass of the star. That will determine the fate of the star. That's the most important parameter for the star, its mass and its chemical composition. Yeah.
Okay. Next question coming up from Atufa Vora. She says that if Betelgeuse goes supernova, the shock wave will pass without hitting Earth. I'm curious, hypothetically, if the shock wave were somehow stronger or extended beyond the expected range, what effects could it have on Earth or solar system?
Yeah, so what is the shock wave? The shock wave is basically made up of charged particles and radiation, right? That is what the shock wave is, which is going to hit, but like I said, the killer zone is 10 parsecs. This star is much, much further away, so it won't be doing that. But typically, if it was closer, it could disrupt the atmosphere of the Earth. It could disrupt it and obviously mess it up. But like I said, we are far enough from it that it's not going to happen. But like I showed you earlier, when the sun becomes red giant itself, it's going to swell up. And in that swollen state, it's going to go beyond the orbit of Saturn. So that includes our orbit. So we'd be also within that. So we don't need a supernova blast. We have the sun who's going to actually do it. When it becomes a red giant, it's going to expand and come up to the orbit of the Earth and even beyond. But like I said, it's after 4.95 billion years. And by then, if either we be stupid enough to finish ourselves off, if we are smart enough to survive that, then we would have already thought up a plan of action to, save ourselves if we survive. Yeah.
Okay, the next question. How similar to speckle imaging is corrective optics technique?
Okay, thank you. That's also a very good question. So speckle imaging, like I showed you, is these short images which you take. Like I said, I'm moving my hand, right? You take shots of my hand in different places, and then you stack them up together so that you get a neat thing, right? In adaptive optics, I think you're talking about adaptive optics or active optics. What is done is that you put an artificial star. Okay, so basically you put a laser beam up in the sky, and you look at that laser beam, and you see how does the laser beam gets distorted because of the atmosphere, right? So then what you're looking at star, you do the reverse process of that to the light of the star, because you've already seen it with a model, artificial star. How is it getting messed up because of the atmosphere? And then you do the reverse of that, right? And with that reverse of it, you can actually get back the original image. Right. So all these techniques have different, positive and negative things to it, in the sense of what is the most appropriate and what is the most. For example, the 30-meter telescope, right? These big telescopes, most of them have this is what is called active adaptive optics. So for example, in the 30-meter telescope, the telescope is made up of basically 392 segments, okay, pieces. Okay, and each of these pieces can be raised, can be moved. Okay, so what is done is that you look at an artificial star, you see what is the image become of it, and these are called accentuators. So these accentuators, which are there under, just think of it, you have these individual mirrors of 1.4 diameters, 1.4 meter diameter. So you add these accentuators and you kind of change the curvature of the telescope so that it can correct for the distortions which are being caused. Okay. Now these are very small corrections. These are like the size of your hair. It's at a very small scale, but you actually have these things which can do it, and it has to do it very accurately, because the problem is that the atmosphere is not constant. Okay. So even if you change the distortion on your mirror, right, the atmosphere turbulence is going to change so fast that you need to be changed this at the scale of microseconds. Right? So that is what is called active optics, where you actually change it so fast so that it can correct for all the distortions happening at the atmosphere at the rate at which the atmosphere is doing it. Right? So what happens is that different wavelengths in different conditions, different things are employed. Depending upon the kind of telescope you are using, you opt for whichever techniques. So that kind of varies. Which one would you use? But there is active optics, adaptive optics, as well as speckle imaging. All these different techniques are there. See, and another problem is also the brightness of your source. For example, Betelgeuse is so bright. So if I take a 60 millisecond exposure, I will get enough of photons to actually get something like an image, right? But if I'm, for example, so therefore for Betelgeuse, speckle imaging works very well because it's very bright, right? But if your star is not so bright, and I take a 60 millisecond or a 10 millisecond exposure, I may hardly get anything. I may not make any image only because that object is not so bright, right? So in 10 milliseconds, I don't pick up things so fast. So for example, for Betelgeuse, this technique is what is important or good because it is a very bright source. So if your source is so bright, then it's good to do speckle imaging. But in general, often the sources we look are not very bright. So then obviously active adaptive optics is better. Yeah.
Okay. So the next question is from Akash Kumar. He says that he has a doubt like what new questions or future research directions do you think this event has opened for astronomers and students interested in studying stellar evolution?
Wow, thank you. Thanks so much. I'm now remembering all the things I did not talk about, which I should have spoke about. So, other than Betelgeuse, there are a bunch of other stars which are also red giants, which we know in the sky. There's Aldebaran, Arcturus, many of them. So, the question is that when we look at their pulsations, we know actually through other means that generally massive stars do have companions. The more massive the star is, the higher the chances of finding a companion. So the question is that even when we look at these other stars, right? Now, if we know that probably this is the case, then when we are looking at these other red giants, etc., it is possible that even they have companions, which was not something that was being explored earlier. People thought that the variation was just happening because of pulsation, right? But now, since if this is true for Betelgeuse, we obviously have to consider such a thing for the other red giants, which we also observe. And like I told you, a very important thing being massive stars are often binaries. And evolution of stars is different if it is an isolated star compared to if it's a binary star. Because in a binary star, what happens, for example, Betelgeuse and this one, stars have what is called the Roche lobe, okay, the tidal radius, etc. In short, don't worry about that. But basically, if you have a binary star, then binaries can exchange mass. Okay, they can exchange because they're close to each other. So as the star is swelling up, right, and it's so close to the other star that the other star can actually eat up some of its mass. So we know that there are stars which Algol, etc. There are stars which actually have exchanged mass with their companions, and because of that, the whole stellar evolution process for such stars becomes different. Because if you exchange mass, you are changing your mass. So you start off with an initial mass of something, but then due to whatever reasons, your mass changes. And if your mass changes, then the normal stellar evolutionary tracks, which we draw on the HR diagram, that is basically followed for a single star. But if you have two stars, then the whole story becomes different and much more complicated. So, then, I mean, stellar astronomy becomes even more interesting and more fun, because then you also have these binaries and you need to worry about if they have they already exchanged mass? If they have exchanged mass, then what was the initial mass? How much exchange has taken place? And, what all has happened. So it makes it more fun and more interesting. Yeah.
Okay. So next question is from Atharv. Kindly ask your question, Atharv.
So first of all, thank you, ma'am, for this great session. I have two questions regarding this session. Ma'am, my first question is, what is the difference between the gravitational wave and shock wave?
Okay. Okay. So a shock wave is, when the supernova takes place, there's a boom, right? And a shock wave is typically a wave which is moving at a speed which is larger than the speed of sound, right? So 330 meters per second, or whatever you take it for. So a shock wave is a wave which moves larger than the speed of sound. Hence, it is called a shock wave. Okay. So that's typically what you get from objects, for example, a supernova, which goes boom like that. Okay. A gravitational wave is, in principle, the distortion of space-time which is caused due to a mass, right? So from Einstein's theory, we know that if you have a massive object, this is like if you have a sheet, right? And I put a ball inside it, the sheet gets distorted because the ball is put inside it. So there's a dip which comes because of that massive ball, right? So what is basically happening is that you have a distortion in space-time taking place because of the presence of this mass, right? And the typical gravitational waves we detect is basically, supposing if you have a merging of two neutron stars or two black holes, they are very massive. And therefore, as they merge together, as they move, you have this distortion, but with this distortion, it becomes like ripples. It becomes ripples because just think of it, if you just have this thing causing a dip, that's fine. But now I have these two guys who are spiraling into each other. They are either two neutron stars or two black holes or whatever they are. And because of that, the distortion in space-time is kind of changing. It creates a wave. And that is what is called a gravitational wave, which is caused in distortion in space-time. So that's quite a different thing for a shock. A shock wave is a normal mechanical wave. where you have particles which are moving with a certain speed and they push something. That is a shock wave. A gravitational wave is this distortion of space-time, right? So they're two different things. Yeah. You wanted to ask something else, right?
Oh, yes, ma'am. Ma'am, my last question is, what physical process cause Betelgeuse outer layer leads to the formation of so many dust clouds, and how does it affect the star's evolution?
So, can you just repeat it?
Like, ma'am, Betelgeuse outer layer leads to the formation of so many dust clouds. Ma'am, how does this affect the star's evolution? And how does it affect the Betelgeuse evolution?
You mean to say this outer layer when you throw it out?
Yeah,
Yes, ma'am, the dust coming out of it.
dust which has come out.
Because it's chucked out. It throws it out. Now what is left is only the core. And the core will either form a neutron star or it will form a black hole. But what the star has chucked out, it's chucked it out. That's okay. It doesn't do anything to the evolution. It's just thrown out, right? What is then important is only the core, which is the central part. Like I said, for the sun, it becomes a white dwarf. And in this case, it would either be a neutron star or a black hole, depending upon, again, how much of mass of Betelgeuse is finally left, right? How much will it lose before it comes to
Ma'am,
that?
ma'am, is there a strange matter in a neutron star core?
Sorry?
I found some people say that there is a strange matter inside neutron star core.
No, in principle, there isn't a strain. It is what is called in a neutron star. It's basically what we call neutron degeneracy. Okay, you don't have atoms and molecules. You have neutrons in a degenerate state. That is it. There's no strange, but it's strange in the sense. Uh, uh, I can't be explaining degeneracy just now to you, but basically degeneracy is when you're kind of violating Pauli's exclusion principle. Okay, so in Pauli's exclusion principle, you can't have the same quantum states for two electrons, which is what is happening in a white dwarf. White dwarf has electron degeneracy, but a neutron star has neutron degeneracy. And therefore, when we write our normal equations of state, right, for any form of degeneracy, the equation of state, etc., becomes different. It is not like what we normally do for our normal matter. So in that way, we can call it what is called strange matter, because it is going through degeneracy. You can Google and read up a little bit of degeneracy, but in short, degenerate material behaves in a different way, in a strange way. So you can call it strange. Yeah.
Thank you.
Welcome.
Okay, so the next question coming up from Tanuja.
Yeah.
Tanuja, please unmute yourself.
Uh, Good evening, ma'am. And first of all, thank you for the informative session. My question is that since you talked about that the high mass stars convert into either they convert into a black hole or neutron stars, as according to my knowledge, there are there I know like there are two types of neutron stars, mainly commonly known as one is the pulsars and the second are the magnetars. So could you just explain why the pulsars spin so fast and magnetars they have such a strongest magnetic field in the whole universe?
Okay. So basically, what's happening in the case of a neutron star, which is also what happens in the case of a black hole, is that you have this core. Okay. Like I told you earlier, basically in a star or even in this core, you have two forces. One is the force of gravitation, which causes it to collapse. And the other thing is the nuclear reactions, which cause it to expand, right? Because you have this reactions taking place in the center, it kind of expands. So you have these two forces. But now when you have a supernova taking place and the core is left, now you don't have any outward gas pressure, right? Because you're not doing any nuclear reactions. So the only force you have is the gravitational force, which is causing it to collapse, right? So it shrinks. It shrinks. And you won't believe it, but the size of a neutron star is barely 10 kilometers. You stay in Jaipur?
I
Where do you-
actually stay in Maharashtra, ma'am, in
Oh,
India.
but wherever you stay, I'm sure you know that 10 kilometers is really, really small. It's very close by, right? I'm sure
We are talking about the stars.
to work, I go more than 10 kilometers. So it's really very small. So generally stars are really huge, right? But because of this gravitational collapse which takes place, because there's no outward force, it becomes a very small star, which is only 10 kilometers, okay, a neutron star, right? And therefore, what happens is all the magnetic force, which was there spread out into this larger size, now becomes very small. And basically, it's an iron, it's a piece of iron, okay, because the star has fused everything up to iron. So just think you have this big, huge iron piece, which is only 10 kilometers in size, which has been contracted, right? And because it's contracting, there's a rotation, right? So when there's a rotation of charged material, that's obviously going to create a magnetic field, right? And because this size is so small, the magnetic field becomes very, very large. And therefore, what basically happens in a pulsar is that because you have this very strong magnetic field, light cannot be come out from the star itself. It only comes out from the poles, right? I can show you a picture over here. Pulsar pic, for example. So you'll basically see that it's often called the torch model. Okay, so it's like a torch where you only have light coming from the. Oh, okay, yeah, I can show it to you here. I can see this 1 minute. I'll just try to do this if I can. So you can you can see in my browser. You see this. So this is typically how a pulsar looks because of the small size. This is the can you see my screen?
Yeah.
You have this magnetic field, and from here light cannot come out because there's total magnetic field. So light will only come out from here or here. Now think of this thing is rotating. It's like a rotating torch. Okay. So depending on where the observer is, whether you are here or whatever, you will just see pulses of light. You will not see light constantly because from the rest of the surface of this object, light cannot come to you, right? It will only come if you face these 2 points, right? So whenever you face these points, you'll see the light and you'll see the pulses. Therefore, it's called the pulsar because you actually end up seeing pulses of light, okay? You actually end up seeing pulses of light which are coming from the top and down. So that's the pulsar. Okay, in a black hole, the mass is even more, and therefore you collapse the size of the neutron star, but you can't even stop further collapse. So it further collapses to give you what mathematically is a zero size, which is nothing but the black hole. So you'll collapse, and then you'll get it like that. Is that what you asked, or you were asking that, right?
Yeah, it is correct the answer, but I was actually asking the why do they spin? Why do these stars
So
spin?
actually spinning is a very easy thing because when you have this contraction taking place, the chances that the star is stationary is very low. Most probably it's moving, right? And you know by angular momentum, ballet dancer thing, if you become contracting, you will spin faster. So the probability that a star will have zero spin is very low. Most probably it will have some kind of a spin, and the spin will just increase when it collapses. So that's it. So because the
Okay,
probability of your finding a star with zero spin is very, very low. It will have some kind of this thing. Yeah. So
thank
that's
you.
how you do. Welcome.
Okay. So the next question coming up from Piyush.
Yeah. Am I audible?
Yeah,
Yeah.
yeah. Go on.
First of all, thanks, ma'am, for this important session. There are so many information that we captured from this session. My question is related to like I have two questions. First is related to dark matter. Second one is related to universe. So how this supernova explosion will help us to identify dark matter and dark energy as of now, whatever we know? Can we explore more about that with the help of this supernova explosion?
Okay. So supernovae are very important objects because they are very bright, right? And they are what we call standard candles. By standard candle, in the sense, through theory, we know what should be the brightness of a supernova. Okay. And therefore, what is done is that to find the distance to faraway galaxies, right? The best way is through a supernova. So if you can find a supernova in a faraway galaxy, you can use that to actually find out the distance to that galaxy, right? Now, how are dark matter studies done or dark energy? Dark energy studies are done how is that, you know, Hubble's law, V is equal to H into R. That means the velocity with which a galaxy is going away from you is equal to Hubble's constant into the distance to that galaxy. Okay. So it is assumed to be a linear law. You're seeing that this expansion is happening, right? But what happens is that if you actually put in the distance which you get from the supernova, and you actually put in the calculate the velocities which you're getting, we actually find that there is an H dot. That means Hubble's constant seems to be increasing. There is an acceleration. Normal expanding universe, we assume that galaxies, the further they are from us, they move with a larger velocity. And Hubble's constant is a constant, right? But now with supernova data, this is a very important piece of data for which even a Nobel Prize was given. People used supernova data, substituted into Hubble's law, right? Velocities we get from spectroscopy, okay? So if you do spectroscopy of the light from a galaxy, you can get the velocity to the galaxy. And then if you have a supernova in that galaxy, you'll get the distance to the galaxy. Then when you calculate Hubble's constant, you see that Hubble's constant is changing. So actually what people found is that the universe is actually accelerating. Okay, it's not exactly a constant velocity. When we thought it was expansion of the universe, we actually now found through data. I'm just checking which year's Nobel went for that. So this is 2011. Okay, so 2011, people got the Nobel Prize for actually discovering that what do you say? That the universe is not just expanding; it is accelerating. Okay, so the question was, why is it accelerating? And the answer to that was given as dark energy. There is some dark energy due to which acceleration is taking place. This is the opposite of gravity. Gravity would have caused the collapse of the universe, right? It will cause it to this thing. But here we have this opposite thing happening, which is causing acceleration. So this is like negative gravity, okay? And people didn't know what name to give to it, so they called it dark energy, okay? So supernova data is very, very important. I mean, the whole accelerating universe, if you read about it, the 2011 Nobel Prize, the basis of it was supernova observations, because supernova are so bright that you can actually use it to look at very far away galaxies. So that's why even there are citizen science projects, Amoli is also part of them, for actually looking for supernovae, because we actually are looking for supernovae because they can add into our data for the dark matter, dark energy estimates. Okay, dark matter is a different thing. Dark matter is the regions on the outskirts of our galaxy where we see that there is gravitating matter, but that is gravitating matter. Dark matter is gravitating matter, which shows its effect in gravitation. But dark energy is kind of a negative energy kind of a thing, for which supernovae have played a very, very important role in their discovery. Yes, so it doesn't just concern stellar astrophysics, it's also concerns cosmology. So this is actually a field which is called observational cosmology. That means you're trying to do cosmology using observations. And yeah.
Thanks, ma'am.
Okay.
My second question is, what about
Yeah.
means how this help us to understand how this universe comes in picture? Is the Big Bang is the only thing, or any supernova also shows us some proofs about this universe starting point like that?
No, in principle, actually, supernovae don't tell you that. It's just the story of stellar evolution. How do stars evolve? How do massive stars evolve? What do they do? Because you know that basically stars are the ones which are generating material in the universe. You know, all the heavier elements, amino acids, all of them are being generated inside stars, and then they later on fuse to form other materials, etc. So in that way, and then basically stars, when they form itself, they form with planets, right? Planets and stars form at the same time. So life forms on those planets, right? So therefore, if you're studying origin of life, etc., the story starts with the origin of the star, because when the star is forming, the planet forms, and then the life comes on the planet, right? So in that way, it's intertwined with this thing, but not exactly with cosmology in that sense. Not like that. Yeah.
Thank you, ma'am. Thank you very much.
Could be indirect, but not direct. Yeah.
Got it.
So the
Thank you.
next question is from Krishna Singh. He says, I have read about the so-called mass gap problem, the apparent lack of compact object between about 2.5 and 5 solar masses. I was wondering, is there also a similar kind of gap between the maximum mass of the white dwarfs and the minimum mass of the neutron stars? And more broadly, how do current observations and stellar evolution models explain these gaps across the different stages of compact object formation?
Oh, okay, that's quite a complicated question because I actually don't even work in compact objects. So I do not know this very well. But generally, there are certain gaps. So there's some, there's a Chandrasekhar limit, which is there for white dwarfs, etc., for neutron stars. So there are certain physical processes which will dictate the maximum mass you can have of a white dwarf, or for example, of a neutron star and things like that. But we know that there could be fluctuations in that also, depending upon the composition of the star, depending on the chemical composition of the star. Even the Chandrasekhar mass, for example, can vary if the mass of the star varies, which can vary depending upon the kind of nuclear reactions which have happened on that star, right? So you could have variations and all that. So yes, that's very, very strongly intertwined with the different stellar processes which are taking place in stars and things like that. And yes, but I'm sorry, but I don't know too much of those detailed things. I know these basic ones, but they are obviously interesting to study because they give you a very good insight into what are the kind of stellar processes, etc., taking place, and why should you be having gaps. Yeah. So if you're trying to study it, it's an interesting thing to study. You should study it. Yeah.
Yeah. The next question from Akash. Kindly ask your question, please.
Good evening, ma'am.
Good evening.
Ma'am, my question is, you use a line in your slide that mass is the key driving of stellar evolution. More massive star evolve faster.
Yeah.
Because mass determines how quickly a star evolve, do small difference in a star initially mass significantly change its end stage? For example, whether it's become a supernova, neutron star, or black hole.
Sorry, can you just repeat the last part of you? You're asking me how does the mass determine the fate of the star?
No, my question is that because mass determines how quickly a star evolves, do small difference in star initially mass significantly change its end stage? For example, whether it become a supernova, neutron star, or a black hole?
Yeah, definitely. So that's what I was talking about earlier also, that's why the normal stellar evolution studies we do are for single stars. But then when you have a binary star, for example, if this is the Betelgeuse case, and Betelgeuse has already exchanged or will exchange mass with the companion, then obviously its evolution will change. Yes, it will definitely change. Its initial mass is something, but then later on what it gains, obviously that changes its evolution. Yes. So, yes, if the mass of the star will change, the fate will also change. Is that what you want to know?
Yes, ma'am. And one more, ma'am, that
Yeah.
we learned that mass play the main role in how a star evolved. If massive star like Betelgeuse lives shorter lives, what lesson does that teach us about the balance between like energy, time, and evolution in the universe?
Yeah. So actually, what happens is that, agreed, these massive stars, they evolve very fast, right?
Yes.
So, but still, there's a lot of, the luminosity of stars. We end up seeing the ones which are the brightest stars, right?
Yes, ma'am.
But the underlying thing is that, like I should have put a slide on that. What nature does is nature basically produces more low mass stars than high mass stars. So most of the mass of the universe is sitting with low mass stars. But the brightness, the luminosity of the universe is basically the high mass stars. So the high mass stars are contributing to the luminosity, while the low mass stars are contributing to the mass, right?
Okay,
So
ma'am.
we have a different role to play in that sense.
Thank you, ma'am.
Yeah.
Okay. Ma'am, I would also like to ask you something. Ma'am, you said that Betelgeuse is a variable star.
Yeah.
You also said that it is a pulsating variable. So can it be in both ways? Like, are there many stars like this, which are variable stars as well as pulsating?
Yeah. So typically giants, all the stars on the right of the HR diagram, they're all giants, and most of them are pulsating stars, basically because you have nuclear fusion taking place. And like I told you, the star, as the fusion takes place, it swells up because there's a lot of energy given out. But then when it swells up, the star becomes cold. So then the nuclear fusion falls. So then it compresses. Then again it swells up. And this happens at a reasonable pace. Actually, even the sun has an oscillation period. But since the sun is main sequence, it's not a very visible one. But the giants, they're typically pulsating stars. Yes, they're typically, most of them are pulsating stars. And pulsation basically means that it's because of the variation in radius. But a star can be variable for many other reasons other than pulsating, right? Like they could have sunspots on them that can cause the pulsation, or maybe it's a binary star, so therefore you have variation because of that. So there could be different reasons for pulsation, but giants are typically pulsating stars. Cepheids, all of them are pulsating stars. Yeah.
Yeah. Ma'am, does the pulsation has changed for Betelgeuse after the dip?
Yeah, I think I showed you that plot, right?
Yeah.
After the dip happened, then for some strange reason, the 420-day cycle was not observed. So yes, so that was the worry, that what happened to it suddenly? Why is it not doing that? But probably it is. Probably because it is expected that the dimming, the companion probably played some kind of a role in the dimming, right? In the gas, etc., which came out. And probably that caused a change in the pulsations, right? Because the amount of material out there kind of changed. And maybe at present it is not in a settled form. See, when you have a perfect, nice 420-day cycle, it's kind of settled down and it's happily doing its 420 days things, right? But now it's kind of got disturbed. So it's probably, it's brightened up. It had faded, but it has brightened up. So that dust has dispersed. In short, that means that the dust is no longer there. That has dispersed, but the star is still in a disturbed condition. Therefore, it's not doing its 420-day cycle. So probably the companion and the gas and all, there's something did happen which did that. But we do not know all that very well as yet as to how did all that happen. And like I said, that even this companion detection is a 1.5 sigma thing. We have to be prepared that after 2.5 years, in November 2027, when we see, we really do not know what will we find. Because then when there are going to be many better telescopes which are going to be looking at it with much more well-planned techniques. And let's see what we find. You could have one companion, you could have two. Who
Ma'am,
knows?
could it be that the companion which we are thinking of is the dust which has been thrown out from Betelgeuse? Could it be that?
No, but then you won't image dust. You won't be able to image dust, right? There's an image, the image which I showed you.
Yeah.
Which is, but it's cold. It's cold. It's cold. It's not hot.
Yeah.
Young stellar object. It's a cold object. Yeah, it could be something. It could be actually, like I said, if you are truthfully saying that you want at least a 3 sigma detection, then we really need to see the data we get in November 2027 to see. But at present, the whole astronomy community is very excited and thinking, oh, probably it is a companion. Because the position and all is exactly what was predicted by the earlier parties, right? What they predicted is exactly the same position. And, all that fits in very, very well. So people are kind of tempted to believe that that's right. But you could have, nature is very exotic, right? I mean, it's science. I mean, I think nature is much more surprising than science fiction itself, right?
Definitely.
So, we really don't know what's in store. So let's see. We'll see what it is.
Okay. So with that, thank you very much, ma'am. And with that, we would like to bring an end to this session. Wonderful session, and really so insightful knowledge about the Betelgeuse and its the companion stars. I think so most of us never knew about that companion stars, the Beetle buddy. So I would just request all the participants present to kindly switch on the camera for a lovely photograph.
Yeah, there are many of them, right?
Yeah, there are. Kindly switch on your cameras, please.
Welcome to everybody. There are many people writing thank yous.
Yeah. And there is one more announcement that you will be receiving your e-certificate after the session on the 10th of October. That is the last day of the World Space Week. You'll be receiving those certificates, but you need to fill the Google form, which will be sent to you on the mail.